All right, hello there, everyone. This is my video lecture notes for CIS352, Spring 2026. These are for the notes yesterday, that is January 22nd. We are talking about lists and recursion over lists in this lecture. So first I talked about list literals. So this is the empty list. I also talked about symbols. Symbols are deduplicated strings. So if I have tick foo, that's kind of like a string foo, except no matter how many copies of tick foo that I have, they'll all map to the same actual location in memory. So I won't be storing a million copies of them. I'll just maybe have a million references to the unique foo symbol. Okay. Then I've got lists here. So in this case, this is the list of symbol XYZ. Notice if I didn't have the quote, then it would be the application of the function x to the identifier y and z. Since I have the quote there that says stop interpreting code, start building data. Okay. We talked about the fact that lists have this inherently recursive structure. So what I mean by that is that the list 1, 2, 3 is actually kind of a nested structure of cons of 1, cons of 2, cons of 3, empty list. And this sort of recursive structure inherent to the list as a data type gives us a template for how to write functions that work over lists. And the template is basically something that's reminiscent of sort of a for in loop, if you're used to programming a language that offers this style of iteration loop over a collection. So in this case, I'm saying for x in the list, and then I'd be accumulating some value. So it's not literally any for loop. That's kind of a reduction, but it's some intuition to begin with. So one of the simplest functions we can write is the length function. So here we say if the list is empty, the length is 0, right? So that's our base case. Otherwise, what we're going to do is we're going to call the recursive call on rest of the list. It's always going to be rest of the list in this primitive recursive style, which is one of the styles for writing recursive functions. We're going to take that result from calling length of the rest of the list, which gives us the length of the rest of the list. And because we are a consel, well, we know that our result should just be 1 plus the length of the rest of the list, right? Okay, so that kind of generalizes to this recursive template here. And this is the primitive recursive template over lists. There are various names for this, but basically the idea is it's a cookbook technique for writing any recursive function over a list. What you do is you check to see if it's empty, right? So a list is either the empty list or it's a consel of some first value that you're prepending onto the rest of some other list. And so a list is always like cons of cons of cons of cons of empty. It's never anything else. It's always either cons, where the first thing is some value and then the rest is some other list, or it's just empty, right? So if it's empty, that's the base case. All right, so that's being able to look at the whole thing. You can see the whole thing, and now I've seen that it's empty. In the recursive case, I can't look at the whole list at once. I've only got the first consel. And so to be able to make the rest of the processing manifest, I actually make the recursive call on the rest of the list. This is this notion of what's called primitive recursion. It's this idea, or structural recursion. It's this idea that we can recur structurally on a smaller sort of subordinate argument, right? And in that way, these kinds of functions, the primitive recursive functions, they always terminate. The reason they always terminate is that there's a clear measure that's getting smaller. And so if we start with finitely sized data and we're always getting smaller every recursive call, well, then eventually we're going to run out of the ability to, do that anymore. We're going to run out of fuel, let's say. And so for that reason, these kinds of functions that are recursive on rest of the list have this kind of property that they always terminate, right? So there was an open question, which is basically, can you write any function in this style? And the answer is no. This is kind of related to things like post theorem and computability and things like that. But a large class of functions are structurally recursive, and it's a good sort of thing to learn as we start, Okay. So we defined some other functions. I had the class define sum. I did some quick answers. I got back an interesting solution. This looks pretty canonical. In this case, I say if it's empty, the sum should be 0. Otherwise, it's first plus the sum of the rest. Okay, that all makes sense. We define exists, huh? Exists, huh, basically says, is there some element x in the list L? Here we're going to say if L is empty, it's false. This was another quick answer, by the way. Otherwise, we can check the first thing and see is that equal. If it is, it's true. Otherwise, we're going to check the rest of the list. Okay, so that makes sense. There's an interesting one called lists equal, huh? This is a harder one because now there's 2 arguments. And because there's 2 arguments, now the question is, which one are we recursive on? Are we always recursive on the first one? Are we always recursive on the second one? Are we kind of recursive on both of them at the same time? Well, the answer to that question actually is a little bit weird in this case because it really doesn't, there's a variety of ways we could do it. We could check L1 and then compare the beginnings of all the L0s or something like that. But to step back, we're going to need to answer a few questions. So when are 2 lists equal? So they're equal when they're pointwise equal on all of their elements, right? So lists are equal when they're pointwise equal, i.e. agree upon length and share the same elements. So I wrote an implementation in class, which is a little bit tricky. In office hours, I discussed kind of a slightly easier solution. So maybe I'll discuss the easier solution first, and then I'll kind of go back to the one that I wrote in class. So I make the problem a little bit easier by saying that 2 lists are equal, L0 and L1, whenever first their lengths are equal, and then this second helper function called L equal huh returns true. Now L equal huh is going to be a slightly simpler function because it's going to assume that the lengths are equal. And if you assume the lengths are equal, then you end up in this scenario where we still write the sort of primitive recursive template. We check L0. If L0 is empty, then by assumption, L1 is also empty. Why? Because I told you the assumption is that they're the same length, right? So the precondition of this function is only valid whenever the lengths of the 2 lists L0 and L1 are equal. But assuming that's the case, then we know here that L1 is also empty. And if L0 and L1 are empty, they're both the empty list. And the empty list is equal to the empty list, so this case should return true. Okay. The second case is the more interesting one. So this is the case where both L0 and L1 are not empty. Neither of them is empty. So what happens then? So then the answer is basically that both of the first elements need to be equal. But also, if I check the equality of the rest of L0 and the rest of L1 simultaneously, those had better be equal as well. All right? So this is actually doing the checking of the rest of the 2 lists to make sure that they're equal. And so what we're doing is we're basically iterating over both lists at the same time. We're taking off the first element from each, asserting they're equal. When they are, we're then ripping off those first elements, taking the rests of those 2 lists, and then we keep going. And this is a little bit more complicated well, I guess it's a more intuitive implementation than the one that's up here. This implementation that I wrote in class does something a little bit different. It says if L0 is empty, then the answer is whether L1 is empty or not. All right, so if you think about that, kind of gets you where you want to be. And if L0 is not empty, well then if L1 is empty, then the whole thing should be false. Otherwise, we want to check to make sure that these properties hold. The same thing from this L equal here. So this thing that I wrote in class, lists equal huh, this one probably needs to be commented out so that the code will actually run. There we go. This one that I wrote in class kind of interleaves the checking of the length with the checking of the individual item equality. And so it turns out this implementation is, it's probably going to be a little bit faster, right? If you've got both of these lists and they're both 1,000,000 elements each, for example, in this implementation, you have to traverse the whole thing 1, 2, and then 3 times, basically, where here you're kind of only doing it once. And so it's not 1 for 1 exactly. There's some slight differences, but generally I would say this one is doing a little bit less work, but it's more conceptually complicated. It's not doing that much more work. It's only doing, you know, a constant factor more. All right, so now I just want to talk about how to get the project. So over here, I have the auto grader. This is project 1. When you log into the auto grader, you should have gotten an email that specifies your password for the auto grader. Your username is your @syr.edu email address. Not the username, the whole email address. That's your username for the auto grader. And your password should have been emailed to you. If it hasn't been emailed to you, let me know, and then I will make sure it's reset or sent to you. So just showing how you use the auto grader. This is the web interface. What you're going to do, you're going to click here and you're going to get a link, and that's a get link. So to use that link, first we're going to go over to where we want to clone it. Now, in this case, I'm going to do this business with grit credential reject. You shouldn't have to do this if you're a new student to the class, but if you've taken the class before and you've previously logged into the auto grader, you'll probably have some saved credentials from the last time you took the class. And so you want to get rid of those before you do this. So I'm going to do that now. Now I'm going to do a git clone, and then I'm going to do this link right here. So let's see, I'm just going to get rid of this code so I can start fresh here. So here, let's clone. There we go. So I entered my password. I got it right. Now I've cloned the project. By the way, I should only have to do it once. Git saves and caches my passwords. So I can go into 330 at P1. And now I do an ls here. So p0.rkt contains the actual solution, so I'm not going to show that in this case. Let's just make a superficial change to it. So I'm going to touch p0.rkt, or maybe I'll make a superficial change. There we go, a comment. So now let me get add. So every time you make a change, you'll need to get add when you want to push up to the auto grader. Although maybe the first thing we should do is test. So I've already got the solution here. I can do Python 3, and now I'm going to do tester.py, and then I'm going to do -av for run all the tests and run them in verbose mode. So it's going to run all those. All right, so those are all done. Now I get add p0.rkt. I could also do get add dot if I wanted to just add everything in the directory. That might be a little bit easier. Then I can do get commit and then updates to p0 and then get push. The auto grader will tell me when the project is due. In this case, it says it's due in 13 days. Okay, so now I'm going to go over here. I'm going to do submit code, and I'm going to go through the get interface, and I can see that I just made this change. I said updates to p0. That comes from my commit message. By the way, when I type in get commit, I have to add this -m, and then I have to specify a message. That message is just a short descriptive update of what was changed since the last time I, pushed code. So in this case, I just set updates to p0. All right, so there we go, and I can submit as a 352 student. And now the auto grader is grading it, and it will start to test it for a few minutes. So now it's being tested. In a few minutes, we should see our grade. Okay, so we got 100. Okay, so that's basically how the auto grader works, and that should be all you need to know. Hopefully tonight you can go clone the project, and we can talk about it in class. All right, thank you.